All right. Okay. If you're just starting to watch this now, please wait just a second so I can make sure that everything is working. Right. Okay. So everything appears to be good. Let me just make sure I have my charger ready. And by the way, I'm kind of sick. I have like a stuffy nose, so apologies in advance for sick sounding voice. So this time we're gonna go over mostly labs because that's the type of thing that's, well, first of all, most of the huge exam and stuff that may not necessarily be on the chips, because if I just restate what's on the chips, then it's not really helping anybody. All right, so with that, we're gonna get right to it. Great. Okay, so in the very, very beginning, I know it seems like such a long time ago, semester ago, we mostly focus on like an introduction, so differentiating between physical and chemical changes. So we burnt and bent old pennies, which are made of mostly copper, and new pennies, which are zinc with just like a copper outer shell. And even though one of the signs of a chemical change is a new substance being produced, even though it seemed like the new penny produced a new substance when the zinc kind of like exploded out of the copper shell, that was not the case. So it's just another example of how you really have to think carefully whether or not there actually was a physical change or a chemical change. And bending the old pennies, once it was heated up, obviously just physical change because you didn't have any new substances being created. So it's like ripping a piece of paper. Like, it's still paper, it's just in a different form. So it's just a physical change. So after that, we had two groups of apples, and one was just normal, and we just left it out, and we coated the other in vitamin C, either in the form of tablets or lemon juice. And we saw that the vitamin C prevented the apples from browning, and the apples that were just by themselves were browned after a while. And after that, we had a 3x4 laminated chart, and we had iodine vinegar and water, and we had solid, so cornstarch, vitamin C powder, baking soda, and baking powder. And we made every combination possible in this tiny bubbles lab. And some of them produced bubbles, which is a sign of a chemical reaction. And color change was also with iodine and cornstarch, which is another example of a sign of a chemical reaction. And in the thick owl lab, obviously you can't measure the thickness of an aluminum sheet with just a normal classroom ruler. So we indirectly measured it by folding it so that it was the same volume, but it was more compact, I guess you could say. And we measured that with a ruler. And once we found the volume, we could just solve for the height by treating it like a rectangular prism. And we found the volume in several ways by just folding it, like I mentioned. We put it in a graduated cylinder to find the volume by water displacement. And we also used the density of aluminum, and so we could find the mass, we could find the volume that way. So that was kind of an introduction, because when you work with math, then you get, especially when you're dividing, multiplying decimals, you get like more than 6, 7, 8 decimal places. And there's no way that a couple of kids in a chemistry classroom could get that accurate. So that's kind of the introduction to sig figs, as we will see later. And another thing, I'm going over the labs, but if anybody has any questions, please make sure you put it in the chat. If you sign in, I believe you'll be able to submit your questions. That's really the more important priority here, to answer any questions that you might have. Other than that, it's just to refresh what you already know. All right, so later in that unit, we had bags of pennies, and old pennies and new pennies, depending on what they're made out of, they had different masses. So we just had a bag of pennies, and we didn't know how many old pennies there were, how many new pennies there were. But we found that we could get the averages and use this. Oops. We could use this equation, like this system of equations, to solve for how many old pennies, how many new pennies there are. And this is relevant to chemistry because this is what's the type of thing that's used for average atomic masses of the same element. So even though carbon, for example, all carbons have to have 12 protons, but they can have different number of neutrons, which makes their masses different. So you'd have to multiply the mass by the frequency, or how often or how many there are, and you average it like so. And we talked about surface tension with first seeing that staples, which cannot float on water, we had them resting on the top of the water because it was resting on the surface tension that's made by hydrogen bonds. And even though hydrogen bonds sound like it's just hydrogen, it's just because of the polarity of the water molecule that has this kind of bond that forms surface tension. And we also saw surface tension when we were putting water droplets on pennies. So that was another example. And we also, if you got the chance to get a bug, it could also rest on the surface tension. And all these things resting on surface tension, it ended when we put a drop of soap in, which we will talk about later. Okay, so the most important thing, if you don't take away anything else from this, is to just make sure you memorize all of your ions and compounds on the lime green sheet for Unit 2, the Unit 2 cover sheet. It will be so, it's just really essential. You should have it memorized. It's okay if you're a little rusty, just make sure you go back and make sure that you're familiar with it. So, wait just one moment. I have to fix a technical issue. Alright, so that's fixed. So like I was saying, make sure you memorize your ions. This helps when you're writing chemist sentences, as well as any fill-ins. And I was kind of doubtful that the song would actually help me memorize it, since to me that all the compounds sounded really similar. So I'm like, okay, why won't I just confuse one compound for another? But the song actually helps. So if you learn that way easily, make sure you know the song. So more about water. Again, this is just things that we learned. It's on the chip, but this is very important. It's a universal solvent because it dissolves other polar/ionic molecules because it itself is polar, and it has high surface tension, like I just talked about, and a high heat capacity. And we talk about that when we do the water has calories lab, etc. So solutions versus solute versus solvent. So just remember, solute has less letters than solvent. So solute is the smaller part, solvent is the bigger part, and together they make the solution. Okay. Oh gosh. And we had it wasn't a lab, but it was a demonstration where we mixed iodine, which was definitely not pink, with baby oil. And once we mixed it, iodine left what it was previously ionically bonded to be with the nonpolar baby oil, which it preferred because it itself is nonpolar, I believe. So that's iodine's actual true color. And the reason why it's not always pink is because it had an ionic bond with something else before. Okay, so we talked about electrolytes when we tested out the TDS, but that's a bit later. So electrolytes are basically once you put them in water, they can conduct electricity because they dissociate into ions, which must be there to conduct electricity. So salt is an example of electrolyte, sugar, alcohol, examples of non-electrolytes because they do not conduct electricity. So turbidity is another characteristic of water that we talked about in the would you drink this lab. If it was really turbid, meaning if it was cloudy or you couldn't see through it very easily, you probably wouldn't want to drink it. And like in the case of pools, if your pool water is cloudy, then you can fix it with a coagulant, which makes all the little particles clump together, condense together, and sink it to the bottom so you could take it out. And on electrolytes, the more it dissociates once it's put into the water, the more that's what makes it strong. So if it disassociates less, it's a weak electrolyte. And the same concept with acids. If it disassociates into more H plus ions, the stronger it is. And there's strong versus weak acids listed on the chip, so I don't have to go into that. So we also tested TDS in class when we mixed Epsom salt, I believe, with water, and we made, remember we had those hand-powered cranks, and in order to make sure that the hand-powered crank lit up the little light bulb that we had, it had to basically be in a complete circuit, right? So there can't be some random wire that's not connected to the next part of the circuit. So we put 2 alligator clips, not touching, which is important, just dipped in the water to see if the salt water would carry the electricity from one clip to the next, and it did, because we saw the light light up when we were cranking the hand crank on the other side. So that was actually pretty cool. And here's a meme here about Gatorade and Powerade, which are examples of things that have electrolytes. And here's actually a tester of TDS, so it's more compact than what we had in class, but it just cycles an electric current through the water, and to see if it can carry electricity, so to speak. Okay, and here's another old school meme, impact font. Those were the good days. So we talked about how fish were threatened by warm water from factories because they had decreased solubility. So this connects to chemistry because if you increase the temperature of water, the ability to dissolve substances in it decreases. So what that means is if you heat up water, then the oxygen will kind of rise out of it, so to speak. And decreasing pressure also decreases solubility, which is why when you open a soda bottle for the first time, you hear that like fizz, which is a carbon dioxide being able to escape because the carbon dioxide is not experiencing the same pressure that it did. And there's another big thing that we worked on, which was going from chemical names to formulas and from formulas to names. And if you kind of get nervous, like I do sometimes, when you see these things, just remember to stay calm. just make sure that if you're going from name to formula, you have to, unless it's otherwise mentioned, make the net charge 0. And you have to add subscripts so that the charges of each substance balance out. And when you're going from formula to name, it's a bit easier in a sense, but if your substance is something that's not in a column where you could tell how many electrons it has, you have to put its Roman numeral by figuring out its charge from the formula. Okay, so we have, a quick practice. This is from the actual chip, actually. So if you haven't practiced already, or you just like this, like doing this for fun, then you have to put these into chemical formulas and these into chemical names. And so you have lead 2, so you know that one lead has +2 charge, and sulfide. And sulfide is actually one of the ones that you can find the charge of from a periodic table. If you're not familiar with like where all the elements are, it's not that big of a deal. But sulfur, or sulfide, has a charge of negative, negative 2. So really all you have to do is PBS. So 1 lead for every 1 sulfur, because the charges just balance out. And it's really great. Okay, so next we have lithium. Next we have lithium, which is +1, and then we have oxide, which is -2. So this is pretty easy again. You have to have 2 lithiums for every 1 oxygen, and so on and so forth. Pretty sure you guys are familiar with this. Just another technical difficulty. Okay, so that's resolved. And more in-class demonstrations, because that's what people tend to forget. So I know that's what I tend to forget. So we saw milk and vinegar being combined. And it was curdled, which is actually a chemical change because something new is being made. And we saw chocolate milk being separated into the chocolate flavoring and milk, which is just physical because the chocolate was always there and the milk was always there. So next we have everybody's favorite, the precipitation rules, woo, or solubility rules. Okay, so just remember, you might have to predict which substances will be solid and which ones will be liquid. So if you know that a substance has sodium and everything else in that column on the periodic table, then it will not be solid. And the next Na is ammonia. If it has ammonium or nitrates or acetates, it will also not precipitate. And another, so along with that, it's most chlorides, bromides, iodides, and sulfates will not precipitate, meaning they will be soluble. So if you have 2 reactants and you know that one of the products is solid, anything with this is not going to fill up that solid blank. What is insoluble, meaning if you have one of these, if you have a carbonate, phosphate, sulfide, or hydroxide, then you know that whatever that's with, it's taking up that solid blank. Okay, so in the Sorcerer's Stone lab, we had like a rotation of sorts. We rotated the sodium carbonate and all these solutions, and we had one of these as like our home solution, so to speak, and we rotated the rest of these, and we had to predict whether or not they would precipitate. And the way you do that is just like, for example, if you're talking about these two, magnesium sulfate and iron chloride, then you basically you just switch. So then iron goes with sulfate, and then magnesium goes with chlorine. So we know that most sulfates are are soluble, so we know that that's not going to be precipitate. And then Mg is not soluble. Sorry, it's not in the sodium family. And then we have chlorides, but we know that most chlorides are soluble as well, so that would not precipitate. Moving on, sig figs, everybody's favorite, right? Really, just do your math problem like in every other math class that we've ever taken, and then I guess in the end is when you really have to worry about sig figs. So if your most recent operation, like what you did to get the very last answer is so that's what you base your judgment on. So if the very last thing you do is multiply or divide, you round to have the same number of significant figures as whatever number that you use in the problem has the least amount of significant figures. And if your most recent operation is adding, subtracting, then you just round to the whatever number has the least, that goes to the least decimal places. So for example, if you have 10.0 and 12.32, your least accurate measurement is the 10.0. So you would only round to the tenths. So this was actually one of my favorite activities, just chewing gum. It was actually pretty fun. We chewed away the sugar and gum so that whatever was left was rubber. So we could calculate by dividing the rubber part over the entire gum mass that how much percent of it was rubber and how much percent of it was sugar. And I think the big difficulty with those kind of problems on like mini exams and things like that is for me it's just keeping track of what numbers are actually what. So what I like to do is like write out the problem horizontally, like write the numbers out horizontally, even because you're going to put it in your calculator anyways. And under each number, I just like to put like a super like quick brief note. Like if I'm writing down the mass of like the entire gum, I'll just write gum total. And then if it's just sugar, then just sugar. So that should help keep track of things. So we did this kind of dangerous lab with the burettes. So before that, actually, we watched solutions being prepared before and after that by Mr. Bender with a graduated pipette. So you can make a solution to whatever volume or molarity you want it by adding water and making sure that this fits this equation. So if you have a really highly concentrated, stomach acid, and you want to dilute it to a certain molarity, then you can use this formula. And so in the actual activity, we used a burette. We had a burette at our own table, and then Mr. Bender had his base burette. Ours had acid in it. And we put in, once we had gotten the base, we put in an indicator that turned blue in the presence of base. So once we put the indicator in, it was immediately blue, because all we had was base. Makes sense. So then we went back to our table and just very slowly dripped acid into our base until the indicator turned green, which meant that there was an equal amount of, or that there's a neutral pH, so essentially that the acid and base are neutralizing each other. So if we put too much acid, the indicator would turn yellow, showing that the pH is acidic. And if we did have a green solution, kudos to you if you were able to get it. It was olive green, I think was the right one. So once we had that, we knew how much acid we put in, or the volume, and how much base we were given. And we also knew the concentration of the base. So using this same formula, we could solve for the concentration of the acid. Woot woot. But it would have to be, we'd have to make sure that it was neutralized first. Because if we had a yellow solution, then there's more acid than base. So it's not really like balancing out. Okay, so we saw soap kill surface tension, like I mentioned earlier, when we were having a staple that was previously resting on the surface of water drop into the water because we put some soap in. And this is because soap is a surfactant or surface acting agent, which basically the hydrophilic heads of the molecule kind of embed themselves into the surface of the water. It's kind of like a pin cushion, I guess you could say, like poking into the surface of the water. And we saw soap kill surface tension, soap clean when it was forming suds in soft water, and eventually if we added a lot of soap in hard water, and we saw soap scumming in hard water before we added a lot. We saw zest, which technically isn't soap, it's synthetic. We saw it sud in hard water because it's synthetic. And in order to have a more luxurious water experience, some people have water softeners, which are basically machines that cycle your water, like from your pipes, through these resin beads that have sodium or potassium. And as the water flows through the beads, they replace calcium, magnesium, iron, the things that make water hard water. They replace it with sodium or potassium, and you actually have to recharge it because after a while the resin beads run out of sodium or potassium. So you just put sodium or potassium salt. And here's everybody's favorite labs. For me personally, the labs kind of like mixed together because we were like always using calorimeters and hot and warm water and cool water. So this should help differentiate between that. So the very first one we did was water has calories. Because everybody says, oh, if I drink water, then that'll help me lose weight because it doesn't have calories. But they're wrong because water can have calories. Because calories is just another word for energy. So we had 2 beakers on the same hot plate, so same heat source, same amount of heat source, or same amount of heat. And the one had less, one had more water. And the one with less water began to steam vigorously first because there's less heat needed to get each gram of water to this higher temperature. And we found that we could find or calculate equilibrium temperature because you can't just average just the temperatures. You also have to take into account how much water there is. So you have to multiply, just like in penny isotopes, you have to multiply how much there is by the temperature and average it out. So then with hot shots, a really cool lab, we had different types of metals, and your group was assigned to a metal. So we had like aluminum, nickel in our long lab bench. And we calculated the specific heat of the metal by putting hot metal into cool or like room temperature water. We found how much energy the hot metal gave to the water. So we assumed that however much energy the water received is the energy that the metal gave. And of course, it's not perfect because we have other factors like the room's air currents and things like that. So it's not perfect, but we just assume. And by calculating how much energy the water received, we could solve for C with a specific heat formula to find specific heat of metal. So specific heat is the energy required in degrees Celsius to raise I recited that wrong, sorry. The energy required in calories to raise the substance by 1 degree Celsius if it's just 1 gram. So after that, we did melting icebergs to find the heat of fusion. Heat of fusion is just how much energy you need to melt ice. And it's just melting the ice, not raising the temperature or anything like that after it's melted. So you have to start with ready to melt ice, like 0-degree ice. So all the energy is just going towards making it go from solid to liquid. So by doing that, we put 0-degree ice, ready to melt ice, in warm water, and we found how much energy that it took to melt the ice and how much energy the melted water took in. And we found that it's roughly, the ice needs 80 calories per gram to go from 0-degree ice to 0-degree water. So then after that, we start working with fire. Ooh, exciting. And we did a goblet of fire. So we saw butane in the lighter, candles in our little metal dish, and alcohol in a little dropper in a metal dish burn. And we put a beaker over a candle flame, and we saw that the candle flame went out, showing that it needs oxygen. And if you isolate the oxygen source, then you cannot have a fire. And we also saw like this, I guess you could say steam. I don't know what the technical term for that is. The condensation. We saw water form on the side of the beaker, showing that combustion of the candle produces water. So whenever you're like doing a chemist sentence and all of it says is the fuel and combust, don't freak out. It's okay. Just you have everything you need with the word combust. You know that the fuel is a reactant, oxygen is a reactant, and that CO2 and water are products. You got this. Okay, after that, we worked with a clamp type thing holding an aluminum can of cold water over a candle in the paraffin power lab. So we found how much energy the candle flame gave to cold water. And the reason why it was cold and not just room temperature was that if a substance is below or above room temperature, then the heat is going to flow between those two substances until equilibrium temperature is reached. So if we had room temperature or warm water, then the candle and the water would be warmer than the room, so we would lose heat to the environment. But if you have ice cold water and a candle flame, it kind of balances each other out. So the net temperature, I guess, is the same as the room temperature. So that's why we did that. And the way you find efficiency is just you divide how much you actually saw, how many calories you actually saw being produced by the theoretical. So if it's at 100% efficiency, like all the conditions are perfect and there's no heat loss to the environment, there's no like air currents in the room, that's the theoretical power. And as you know, that never really happens. So then you get a decimal, convert that to a percent, get your efficiency. Okay, so we stirred salts in water in the Heat from Nowhere lab in calorimeters, and we measured the temperature change, and we found how much energy was produced or absorbed by the reactants. So even if they're all salts, it can still be exothermic or endothermic. And we saw the Nehemiah bagel story. I was really confused as to what the bagels meant and like why he was happy when he had bagels and running around leaving bagels. Like, I don't know, I was confused, but it's okay. Just imagine, I figured out that really the whole point of the story is just to emphasize that substances can only release or absorb certain amounts of energy in packages. So like we saw, Nehemiah only took certain amounts, like predetermined amounts based on what the substance is or quanta. And because also these specific energy amounts are also applied to what they can release, that's why certain types of light have certain lines on a spectroscope. For example, sodium light is 2 yellow lines. Please don't forget that. So based on the substance, there's different types of, or there's different amounts of energy that they can release. So that's why UV light has 4/5 lines and different, and so incandescent lights, fluorescent, we just looked at these through spectroscopes. The sun, incandescent light, fluorescent lights. We also saw tonic water in people's mouths glowing green. That was really cool. And at the very end, we watched a skit to know that francium is the biggest in terms of atomic radius. So the distance between the very center of the atom and the most outer electron is the largest. And he is the happiest, like it's like a play on words, I guess, because it has the lowest electronegativity, which means it does not want to take electrons at all. And it's the most easily ionized. So the amount of energy another atom needs to rip away an electron from francium is very low. It's the lowest. And these trends, so if something is closer to francium, that means it's bigger than another element that's further away. And same goes for electronegativity and ionization energy. Okay, thank you to the 3 people watching this right now. Okay, and since there does not appear to be any questions, I think I'm going to end it here. Good luck to everybody. Make sure you go to sleep on time, please. That will help. Even Mr. Bender said that. Go to sleep on time. And go over your chips and make sure that you know details and how they connect to the chemistry content that we did. Because even though bagels and a new student seems really, really random, it's actually connected in a kind of smart way. Okay, thanks to 2 people watching, and with that, I'm going to end the stream. Okay, good luck.